Alright, so first let's start by reviewing what we did on day one before we hop into any new items. We discussed units of pressure and how there were three common ones used in science classrooms. There's the standard one is 1 atmosphere. That's pretty much used all over the place because it's convenient and easy to understand. The international standard that is used in physics is kilopascals. And then these two are actually the same. One is the height of the mercury column we talked about. One is just converting millimeters of mercury into a unit called torr, which is named after the man who invented the barometer, Torricelli. We then spent a lot of time looking at the different equations for the gas laws and how you can predict pressures and volume changes and temperature and mole changes. So we have the first three gas laws, Boyle's law, P1V1 equals P2V2. I left the ones off. On each case, this is the one side and this is the two side. So if the pressure increases, the volume's got to decrease. Charles' law was V1 over T1 equals V2 over T2. The one key thing with temperature is it must always be converted to Kelvin. So we have that right here. Temperature is whatever degrees Celsius you have plus 273 to go to Kelvin. So if you have 100 degrees Celsius plus 273, you'd have 373 kelvins. This is a much better scale. It predicts the relationship between temperature and kinetic energy, and it's really the energy of the particles that are impacting all of these changes. Avogadro has a law which is related to moles. N is moles, so that feels weird to some people. Can't type evidently. Yeah, N is the variable for moles. And then we have the ideal gas law, pressure, volume, moles, R, and temperature. Notice there's no changes. It's not like V1, V2. It's one volume, one pressure, one moles, one temperature. And the units could be variable, so we have to be careful with the units. If we're dealing with volume, we always use liters with the ideal gas law. If we're using temperature, of course we're going to use Kelvin. N is of course moles, but that pesky P, the pressure could be in atmospheres, it could be in kilopascals, it could be in torr or millimeters of mercury. So we have three different common unit values for R, and again they correspond with whether it's in atmospheres, torrs, or kilopascals. These values were in your notes. You need to make sure that your units match up with whatever you were given. And the last one we did that's pretty boring and compared to the others is Dalton's law of partial pressure. Probably one of the more useful ones, but it just says all of the pressures can be added together to find the total. This is also true of the moles of gas. We pretend that every mole of gas is identical to every other mole of gas or every particle. So whether it's hydrogen, helium, nitrogen, or oxygen, they're all just gas, so we can add their moles together just like we can add their pressures together. That can be useful. It can save us a lot of steps to add up moles instead of doing it problem a completely different way. Alright, let's look at the next part of the notes, which is pretty easy. Volumetric ratios. These equations that we have, these balanced equations also that represent moles, we would say 1 mole plus 3 moles produces 2 moles. But you could also take those ratios and apply them directly to volumes. You could say 1 liter of nitrogen reacts with 3 liters of hydrogen to produce 2 liters of ammonia. That is assuming some big things though. That is assuming this, constant pressure and temperature. If it's not constant pressure and temperature, you can't do this. So if anything changes, you can't do this. So this is not always applicable, but if they are constant, you can use this. So here we are, we've got 12 liters of water. How many liters of oxygen gas are needed? Again, this should be saying assuming constant pressure and temperature. So for every 12 liters, let's see, it's a 6 to 7 or 7/6 ratio. 6 waters, 7 oxygens, 6 waters, 7 oxygen. So we can do 6 times 7 divided by, sorry, I can't speak evidently. 12 times 7 divided by 6. Well, 12 divided by 6 is 2. 2 times 7 is 14 liters of oxygen should be needed. You could go about this a different way. You could convert volume into moles, do the mole ratio, but when you convert it back to volume, you're going to cancel out the initial conversion from moles and volume and back again, which is why it's allowed to just use the ratio. Standard temperature and pressure. I went over this a little bit in the homework, but here it is also. STP, standard temperature and pressure, is 0 degrees Celsius or 273 kelvins for gases. When we're talking about gases, we always work, that's not how you spell gases, there you go. You always work at standard value. Well, you don't always. If you're working at standard values, then the temperature is 273 and the pressure is a nice 1 atmosphere. That's a little chilly for my sake, that's freezing for water, but this is the standard value that chemists work with gas laws at. If you plug these two numbers into the ideal gas law, PV equals nRT, and you always use those values, so the same pressure, 1, and the same temperature, 273, and the only variables left become moles and volume. And we find out that there is a ratio for every 1 mole of gas, you would have 22 liters of gas. And that ratio can be shown over and over and over again no matter what the gas is. So if you had 1 mole of oxygen, it would be 22.4 liters of oxygen. Again, that's only true because you're keeping, the temperature, R, and pressure the same, and the only things left are volume and moles. So if you put 2 moles in, you're going to get 44.8, which is the same ratio, 1 and 22.4. Once you start seeing a constant ratio, people start to go, well, that might be worth knowing. So a lot of people say to themselves, 1 mole of gas is 22.4 liters, and they can use it all over the place. So in this example here, we see there's 1.75 liters of gas at STP. Well, once we see at STP, we know we've got the standard values, and then we can just use this ratio to go from moles to volume. So they have 1.75 liters, 22.4 liters, 1 mole. Well, if 1.75 liters divided by 22.4, that'll tell us how many moles we have. Pretend there's an equal sign here. And we know how many moles of nitrogen that would be. Example 2. What did they do? They gave us atoms of helium? Well, that's not too unreasonable. We could say, here are atoms. We know the relationship between atoms and moles from Avogadro's number way back. I've converted atoms to moles and then moles to volume. There we go, to 11.2 liters. Not terrible, see? Use your scientific notation buttons on your calculators. We can also apply that same 22.4 into stoichiometry. I see you cringing right now. Here it is. We are taking the mass of zinc, don't use that pen. Thanks, computer. 1.13 grams of zinc, changing that into grams, these grams into moles. This value is, of course, from the periodic table. And then for every 1 zinc, there is 1 chlorine. For every 1 zinc, there's 1 chlorine. And if it is at STP, we can use the conversion from volume to moles. I'm going to pause so I can do the math in my calculator. So I just did the math in my calculator. I got 0.387152. I'm going to think about sig figs. I have 3 values here, infinite, 4, infinite, 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 and 3. I'm going to go with the first 3. Let's see. Click on there. 0. Remember the zeros to the left don't count, so I haven't typed an actual sig fig yet. There's the first one, there's the next one, there's the third one. And this is not grams or equal sign, this is liters. Alright, there we go. Got the volume. And then what if it's not an STP? Well, here we did mass to moles, moles to moles, and then we could go ahead and use the 22.4 as 1 liter. But if it's not an STP, we can't use the 22.4 liters. So what did I do in the last example? Mass to moles, moles to moles. Now I know the moles of ammonia, and then I used that in my PV equals nRT. So there's my moles, temperature in Kelvin. They gave the pressure in millimeters of mercury, so I picked the R. There's several R values. I picked the R that was in torr or millimeters of mercury, 62.36. There it is, 62.36. Plug everything in, and I calculated the volume of ammonia, 5 liters of ammonia. Practice, practice, practice. You probably want to pick up worksheet 2 now and see what you can do. Identify your givens, figure out which equation to use. I strongly suggest you put all of these things on one note card. You're going to need to know these equations for the test. So figure out some way to study them. All right, good luck, guys.